Part of waves, or the wave goodbye. Yes, I did think about that, and yes, it did sound better in my head. Talking about waves. Now, we're going to talk about things emitting out from a centre. Here's a bug squiggling around on the surface of water, and you can see the little ripples are going out from the bug. The ripples are the same at A, at B, because the bug is stationary. So the wavelength at A is the same as the wavelength at B. Now, if the bug starts moving in that direction, then the bug is catching up with the waves it's producing by its little jiggling about. So the wavelength felt or seen at B is different from the wavelength of A. The wavelength at B is shorter and therefore the frequency is higher. Whereas the wavelength at A, the wavelength is longer and the frequency is lower. So there's a difference in wavelength and therefore a difference in frequency between A and B. And this depends whether the thing is moving towards you or moving away. And it's called, of course, the Doppler effect. Here it is. There you are, nice mind-blowing. I think it's going to repeat itself. I hope so. There you go. Wow, look at that. And you can see the waves in front of it are much closer together than the waves behind it, which is why we get that as it passes us. So if we are at the edge of the screen, as it's coming towards us, as it passes us, that's the lower note. That's the difference between the frequency of one and another. Now, of course, if you therefore travel at the speed of sound, you catch up with all your sound waves. And as the sound wave passes a person, you get all the sound that the object has made in the previous, few seconds. And that's why you get the sonic boom. It's all the sound coming at the same time because the object is caught up with its own sound. Or it could actually get ahead of its own sound and be faster than sound, or faster than twice the speed of sound. You get two booms. You get the boom as it comes past you and the boom of all the waves at the other side. So excellent, sort of interesting, but this is the sonic boom basically. So the Doppler effect, the apparent change in frequency due to the motion of the observer or of the source, hence the change in pitch, hence that Now this is the diagram you should be drawing. All the elements are here. You have noted that it's a wave crest. You've shown the wavelength between the two waves. You've shown that on the left-hand side with the stationary truck, the two are the same. And on the right-hand side where the truck is moving, and you've indicated the direction of movement with the arrow, you've shown that there's a smaller wavelength, larger wavelength. So this is the entire Doppler effect explained in these two diagrams. You cannot go wrong if you remember all the labels of these diagrams. And you also really should remember the definition, the apparent change in frequency due to the motion of the observer or the source. That's on. Yeah, we already did that. I don't think you write that down. So as an example, you have to say guarded checkpoints. Guarded checkpoints use, this is a use of the Doppler effect. Now, the animal kingdom uses the Doppler effect many times, particularly bats use the Doppler effect, not radar, but bats use the Doppler effect and clicking in order to tell how close they are to objects, etc. Except that's not a use. When they say use in physics, they mean something humans use, not animals. Okay, so what's another if? Well, you can see whether a star is coming towards you or going away from you using the red shift. Well, the shift in wavelength. You can see these tiny black lines called Fraunhofer lines, which are the absorption spectra of different objects, the atmosphere of the sun, things like that. And you can see that these absorption lines are shifted towards the red. And they're absorbed rather than the whole light is absorbed, because you're looking at the spectrum. You see the same spectrum. The star looks the same. What's shifted are these tiny absorption lines, which are in every star due to the helium in the atmosphere. And they are shifted towards the red. That means that it's a longer wavelength. And as you know, from a longer wavelength means the thing is moving away from you. That's the red shift. Now, only one galaxy is blue shifted. That's Andromeda 2. Yes, it means it's coming towards us. And then we've got a bit of time, a couple of billion years, but we should get ready. Okay, so how do we do it calculation-wise? Well, we have a thing. A train whistle emits 700 hertz. Okay, fair enough. What is the apparent frequency if the train is travelling towards you at 30 metres per second. Now, usually they actually give you the two frequencies and ask you for the speed. But this one I've made it a bit simpler because it's where we start. We write down the formula. Hey, it's in the logbook. Who knew? We put the numbers in. The frequency is 700, obviously. The 340 is the speed of sound. Now, if you do this for light, you have to use the speed of light, which is 3 times 10 to the 8. But most of the calculations will be about sound, and so it's around 340. But it's always given in the question, as you can see. C, the speed of the wave, that's the letter we use, little c, for the speed of the wave. So, C, the speed of the wave, is also in there, and V is basically your velocity. Now, it's travelling towards you, so that's shortening the distance to you. And because it's shortening coming towards you, we subtract it from the velocity of the wave underneath. You see? It's subtracted. Now, if it was going away from you, you'd add it. And you get a bigger frequency. Now, you would expect a bigger frequency if it's something coming towards you. It's going to be higher pitched. That's what you should expect. If you get a lower frequency, then you probably use the wrong sign there for the V. Because in the logbook, it's written as plus and minus, and you have to kind of know. But things coming towards you, there's minus. The distance is shorter, so that's why minus. But when we use a formula, we should always write down what each of the letters mean. We should always try to, anyway. When you're actually doing a straight calculation, this is not important. But when you're asked to define something, or when you're using a formula to explain something, you must write down what the individual letters mean. And if you can't remember, that's also in the logbook on a different section. Tuning forks. Tuning fork's great. I love a tuning fork. Got a tuning fork somewhere around here. Let me have a look for my tuning fork. Here we are. This is my tuning fork. Not even sure if you can hear that. I'll have to listen to the soundtrack on the way back. Anyway, basically both prongs of the tuning fork well, that's two sources. If you have two sources, you can have interference. If you have interference, you can have waves. So if we twist the tuning fork near our ear, it goes loud and soft. This guy seems to be really impressed. That's an impressed face, if you ask me. So the two prongs of the tuning fork, and as we twist them near our ear, it goes loud and it goes soft. So the two prongs are interfering with each other. And because of the loud and the soft interference pattern, the loud being constructive, the soft being destructive interference, as we do that, we realise that we've proved something. What have we proved by having interference? We've proved that sound is a wave. Okay, we've proved that sound is a wave. We also proved I didn't turn the sound off on this again. Yeah, there we are. So the summary, sound as a wave. Sound is a wave because of interference, and an interference pattern we can get from a tuning fork from twisting it near our ear. Now, it doesn't work because of reflection. It doesn't work unless it's near our ear, but as you twist it near your ear, you'll get this loud and soft, and that's an interference pattern because they're coherent sources. Now, we can also create coherent sources here by these two loudspeakers attached to the same sound generator or oscillator, and you get exactly the same frequency. So what you'll hear as you go from left to right or right to left, you'll get it go loud, soft, you see? The loud is constructive and the soft is destructive because they're coherent sources. Remember the word coherent? Because they're coherent sources. Loud, soft, loud, soft. And this, of course, is an interference pattern. Loud, soft, interference pattern. The interference pattern of constructive and destructive means it's a wave. Now a bit of, more definition. Sound intensity. It's the amount of energy passing through a square metre. Now, imagine sound is being generated by the speaker. Very close to the speaker, the ball of sound surrounds a much smaller surface area. So if we take 1 square metre of that around the speaker, that's going to be a lot of sound. A lot of the percentage of the sound generated is going to pass through that square metre. However, if we move further away, and not very much further away, and take another square metre, well, a smaller percentage of the sound generated is going to pass through that square metre because there's a bigger square meterage for it to pass through. And this is true the further we go out. So the further we go away from the speaker, the greater the area that the energy from that speaker is spread over. So a square metre window contains a smaller percentage, a smaller amount. So all we have to do is look how much area it's spread across. Well, that's the surface area of a sphere. So what we do to do the actual calculation is we take the surface area of the sphere of which our 1 metre square is part. We work out what that area is. In this case, it's a 2 metre away from a 10 watt speaker. So that means that 10 watts is spread over 50 metres squared. If it was 1, you see, it would be spread over a less. If it was 3 metres away, it was spread over a bigger surface area. But it's the same 10 watts. The 10 watt doesn't change. That's going out. 10 watts. That's 10 joules every second, you see. That's what 10 watts is, 10 joules a second. So it's the amount of watts spread over depending on how far you are away. So all we have to do is we look at the logbook. We say the units for sound intensity is watts per metre squared. So you've got watts. You haven't got meters, you haven't got meters squared, you've got meters, but then you remember, surface area of a sphere. Sphere. I'll try again. Sphere. That sounds better. 10 watts divided by 50, the surface area of the sphere, gives us a sound intensity of 0.2 watts per meter squared. Easy. The amount of energy on the surface area of the sphere. Sound intensity level, possible to understand. It's a logarithmic scale, basically, so that, very loud sounds and very big sounds can be just, written as numbers, which are very similar to each other. It seems confusing, but it's very useful in science. So it's the same as earthquakes. An earthquake, which is a 6 on the earthquake scale, is 10 times bigger than one that's 5. And one that's 7 is 10 times bigger than 6 and 100 times bigger than 5. Now, it's not quite the same on the sound intensity scale because we use E, logarithm of E, instead of the logarithm of 10, which is used on the earthquake scale. So every time we double in our sound, it goes up by 3 decibels. So if you think about that, if you go from 75 decibels to 110 decibels, that's a lot of threes. And that's every time it's gone up by 3, it's doubled in intensity, doubled. So from 75 to 85, that's more than 3 doubles, So that's it's gone up by 8 times, 8 times bigger. So, it's an awful lot of energy. As I say, it's based on sound intensity level and decibels adjusted. Now, we do have something called the decibel scale. Decibels is like 10 bells, basically. So a bell is a small. The 10 there is to multiply everything by 10. Otherwise, it'd be too small a number for us to think about. Lots of things like this in standard reference intensity. Now, you don't actually have to use this in a calculation. You have to know 2 things. One, this idea of the dBA, which is an adjusted decibel, adjusted for the range of the human ear. So it really only takes into account frequencies which a human can hear. And an ordinary human, not like a superhuman. Acoustics. Very good. This idea that if you build something well enough, the reflected sound and the direct sound will form constructive interference. I don't know if you remember Big Bang Theory. Sheldon had his favourite seat in the cinema, and it was his favourite seat because it had the best constructive interference. In most cinemas, they hang drapes, really heavy material, so that there's no reflective sound because you can't get acoustics because they're shaped like boxes. You see the sort of thing you need to get acoustics, the very odd sort of shapes to get good acoustics. Here's another one. You see, this is the best concert hall in London. It's absolutely fantastic, but it's weird design, and it's because of all these acoustics. The idea that you want to have reflective sound forming in every place that you have reflective sound going together with your direct sound to form constructive interference, and where that's impossible, you absorb the sound, which is why there are things hanging from the ceiling to either reflect or absorb the sound. And most halls are done like this. The threshold of hearing. Now, the absolute threshold of hearing is the minimum sound that you can hear at 1 kilohertz. So 1 kilohertz sound, the minimum sound level. So that's the minimum, that's the threshold, the quietest sound. The quietest sound you can hear at 1 kilohertz. Whereas the limits of audibility are the upper and lower frequencies you can hear, which change considerably, particularly as you get older. My limits of audibility are severely affected by going to gigs like the one on the right, which I believe is Grateful Dead. I didn't actually go to that one because it was in Anaheim in 1978. But I wasn't in Anaheim in 1978. I think I was probably in a squat in Sheffield. But it doesn't really matter where I was. The point is that my ears have been ruined. And so the frequency of my hearing response is very low. I can only hear about 12,000 hertz onwards, whereas most adults can hear 14,000. And young people like yourself, often can hear 17, 18,000. Babies can hear 20. Dogs can hear 25, which is why you have dog whistles. You blow a whistle which no one can hear, makes your ears hurt a bit. And the dog can hear it, and it drives them nuts. Brilliant. So, and as I say, that's basically what I'm saying. So the only thing is, limits of audibility, limits, plural, are the two frequencies. The limit of hearing, that's 1, is the lowest sound you can hear. It's book learning, you just have to learn it, sorry. Now, just before we leave this whole subject, to go back to what I said about decibels. Every increase of 3 decibels is a Doppler intensity. So, if you're going from 104 watts per meter squared, that's the sound intensity, to 208, that's a doubling of the intensity. The sound intensity level, measured in decibels, has gone up by exactly 3 decibels. Whereas if you go up from 312 to 1,248, that's gone up by 4 times, so it's 6 decibels. So the left was 70 decibels, 312 watts per square metre. 1,248 watts per square metre is 76 decibels. You see? So there's a huge difference between 70 and 76 decibels. So when we get to 110 decibels, we're talking enormous volumes that are really unhealthy, like standing next to jet aircraft as they're taking off, that kind of thing. So let's just wrap up. I just want to do this again. I found this fantastic slide on the photoelectric effect, and I was going to put it in photoelectric effect and said, no, I won't. I'll be controlled. Photoelectric effect, brilliant slide. I'm going to print this out in colour and put it everywhere because it really explains it perfectly. Red light comes in photons. It strikes potassium. Red light has a wavelength of 700 nanometers. Now, if we convert that to frequency and multiply it by Planck's constant, we get 1.77 electron volts. Now, that's its energy. That's the amount of energy a photon of red light has. Now, potassium has a work function, meaning the minimum energy to release an electron, of 2 electron volts. So no matter how much red light you shine on potassium, no matter how bright it is, it will not release any electrons. Green light is 2.25 electron volts because it has a slightly shorter wavelength, 550 nanometers. So the green light will release an electron, and the surplus energy, the 0.25 of an electron volt that's not needed to release the electron, will be turned into velocity. So the electron will move away at 2.96 times 10 to the 5 meters per second. Fairly quick. Now, the violet light, always all about the violet, is at 400 nanometers. 400 nanometers, 3.1 electron volts. So it's more than enough energy, leaving 1.1 electron volt over. And this turns into kinetic energy of the electron. And so instead of the 2.96 times 10 to the 5, it speeds away at 6.22 times 10 to the 5 meters per second. Brilliant diagram explaining the photoelectric effect. So it's only the frequency or the wavelength which affects whether the electron is produced. Higher the frequency, the shorter the wavelength, the faster the electron leaves the metal. We did this in class. Have a think about it. Try and remember it. If you shine red light onto a red book, the book looks red. If you shine green light onto the book, it goes black because there's no red light to reflect. A book is red because it reflects red light. So it will reflect red light if it's shone on it. If it's green light, which doesn't contain any red, the book looks black because there's no red light to reflect. So, very briefly, last section, reflection, wave bouncing off an object, example, an echo. Refraction, wave changing speed and direction due to the change in density. So changes speed and therefore direction. The frequency stays the same. And an example, well, you can use Snell's law or bone bending. I've used so about people hearing across lakes because when the air is cold above the water, it diffracts the water back down again. Sorry, refracts. Diffraction, the spreading of a wave around an obstacle or on the emergent side of a split. It's better with longer wavelengths. Sound goes around corners. It's spreading from a slit as well. Interference is where two coherent waves meeting combine at any point. It's the algebraic sum of the two waves. And it proves things are waves. Anytime you can get things to interfere, it proves they're waves. You can have constructive and destructive, and they form an interference pattern. Polarization reduces a transverse wave to one plane of oscillation. It's what we say is the difference between transverse and longitudinal. A transverse wave will polarize, a longitudinal won't. And this is why we need snow glasses, because light polarizes when it hits the snow. Okay, you can freeze that if you like, or you can print this out. There's a brilliant little thing like the last picture, very helpful. And this is the question I'm going to set. It's a question 3, so it's a practical question. I hope you find this, it's not question 3, it's a question 7, 2003. What is the matter with you? Oh, but it's an ideal question for revision of this section, I think. I hope. So, I'm going to do this now. I'm going to wave goodbye. I'm waving now. Wave.